So the third lecture, the distributed system, will be about consistency and replication. Yes, so I think we can dive straight into the topic. So the outline today would be to introduce what we mean by consistency, what we mean by replication as well. Why do we need such a thing? Consistency replication. Why do we need them? And then we'll see a few consistency techniques and models, and also we'll talk about replication strategies. We're gonna try to cover a few examples, and then we're gonna try to see them in practice in real life by either seeing some technologies and how they're designed, or we can look at some code. So I think a small recap from the few sessions lead also. I think we've talked about stateful versus stateless. We've talked about the need for establishing guaranteeing consistency, availability, and fault tolerance. I think we've already seen that before. So the reason why we need consistency for distributed system, I think it's quite understandable. Why do we need to manage consistency and replication for distributed system? Is to guarantee and the system is functioning as a single entity, and the main way to the right way to do this is to have some mechanisms they guarantee consistency. As you can see, the more we try to guarantee consistency more, the more trade-offs we need to consider, and غالبا كيكونوا between consistency and availability. Yeah, so CAP theorem, you've seen it before, and I just want to add in case of network partition, a distributed system should basically choose between consistency and availability. And yeah, we've seen this before, but yeah. So I think I guess the motivation is understood for now, right? So we'll dive straight into consistency. So we'll see an overview of consistency models. We'll see three: strict, sequential, and eventual consistency. And we'll see a few techniques for achieving consistency. One of them is lock-in mechanisms, pessimistic lock-in, optimistic lock-in. We'll see if we can find some time to see multi-version concurrency control, but yeah, we'll focus on lock-in mechanisms and the consistency models for now. Questions so far? Okay. Then yeah, we can talk about strict consistency. When we talk about strict consistency, we talk about this term linearizability. Linearizability is to make all the transactions, will make all the updates data all the reads and writes in a nutshell linearizable. Linearizable is perceived in a linear way. Guaranteeing a strong consistency of all nodes, which means all nodes should be able to all the components, the nodes of our distributed system should be able to should have the same state at all times. This is a strict consistency. So one way to guarantee headley consistency is a distributed lock. We can implement a distributed lock, or we can use some tool like Zookeeper to implement a distributed lock, and then we lock a certain resource. We prevent any reads or writes for a specific resource, and then we release the lock, so in the form of a mutex. We will also see like a two-phase commit is an interesting way to achieve this as well. But one question is, how can we ensure the order of execution? What makes us say that this is the order of execution for that? This is the order of execution that should be for all nodes. In a concurrent world, it's a very actually it's a very difficult question. It's a quite difficult question that we will try to answer consensus, but at the same time we'll also have a time chapter about time. We can see how we can have a global time, but for the sake of focusing on consistency for now, we're gonna consider that we have a global time. So one way to guarantee the order of execution is to have a unique time for every transaction, or a unique timestamp for every transaction, or for every action, read or write action. And I think, as you understand, as you can imagine, the more we are trying to achieve this consistency, the trade-off would be processing time and availability. And yeah, I mean, one example that we can think about is banking operations, especially back office banking operations. And they are some of the applications are using, or some of the parts of banking operations are using strict consistency when they're doing critical operations. So yeah, the resources everywhere are locked for that specific resource, or the nodes are prevented from reading and writing to the same resource until the lock is released. Yeah, we can see an example. Strict consistency. Client performs a write transaction. Let's call it that way. Node 1 prepares this transaction by prompting, or by sending a prepare for all the other nodes, and then once all of them were acknowledged this, then we say that all nodes are prepared, and then we commit the transaction, and then we wait for the commit to be done before we flag the transaction as successful. And this is the two phase, or two-step or two-phase commit, where we prepare the transaction, we get a vote from all nodes, or we get an acknowledgement from all nodes, then we commit. Then now imagine a case where node 3 stops, or node 3 disconnects from the network somehow. What can happen here in a strict consistency scenario? Does anybody want to guess?
In which time exactly?
Let's say preparing transaction. Let's say a prepared transaction that we see here doesn't reach node 3. What happens to the transaction?
I guess it will be cancelled because the third node doesn't share.
Yeah, I mean, exactly. So it fails. Transaction fails because something here happened. So I think you can start to feel what the trade-off of strict consistency is in this case. Which is,
it needs time, maybe.
Yeah,
it takes time.
Yeah, I mean, the processing time is higher because all nodes need to do this in the same time. but also availability is reduced. Availability is reduced, and also the probability that something happens in one of the nodes increases as the number of nodes increase. So let's say the fault probability of one node to fail is 1%. If you have 100 nodes, let's say they have independent they're independently they have independent probabilities, which is not the case in real life, but let's just assume that. I mean, the more nodes you add, the higher the chances that one of them will have a problem. I mean, just logically, without going into details. So the more nodes you have, the more difficult it becomes to guarantee a strict consistency or to implement a strict consistency. Okay, any questions here? Okay. We can move to sequential consistency, which is a different way to do things, or with different level of consistency. This is a bit weaker than strict consistency. So this one guarantees the order of operations across multiple nodes or processes, and the results of all executions across nodes should be the same as if operations of all nodes were executed in the same order. So what we mean by this is operations for every individual node appear in some form of global order. But the most important thing is that every individual node sees the sequence in the order of its own program. So it's as if we have a relaxed strict consistency. And yeah, I think we can understand with a small example. So as we said, there is a global order of operations, and this global order is consistent with the order of operations on each individual node. And yeah, I mean, we need to preserve the program order, the order in which operations in each node are preserved in the same order. And then the real-time requirement is if an operation happens before another operation in real time, the order should also be preserved in the global order. Yeah, I think I'll give an example. So yeah, I mean, we can see here node A reads x and sees that x is equal to 0, then writes x is equal to 1, or assigns 1 to x. B reads x, sees it's 0, and then writes 2 to x at a certain point in time. You can see that this is a concurrency problem, right? So can you guess what are the possible values that x could take? I think that's a very easy question.
1 or 2?
Yeah, well, in what order?
I think it's unpredictable. If it depends on the first one. It depends on the order, like the instruction were executed.
Yeah,
But if we,
yeah,
sorry,
go ahead.
Zaman, do we have like a global lock or something like this that would
No.
prevent this from happening?
No, we don't have a global lock law in this case. So as you said, it could be one of those orders. It could be that read x equals 0, read x as 0, and then write 1 happens a long time before this. Before node B changes it to 2, or it could be those. I mean, this one is impossible in our case because read x for node B is also 0, so it's one of those two cases, right? It's order 2 or order 3. So both of them read, and then one of them writes before the second one writes. Who writes before? Sequential consistency says both are fine. It could be that multiple nodes can see can see different orders for the same actions, but the actions for every node should be in the same order. So for example, read x0 and write x1, we know that read precedes write, so they should execute in the same order. That's the most important thing in sequential consistency. That's what sequential consistency cares about the most. So we are hoping that we are fine with some level of uncertainty here, with, of course, higher availability than strict consistency. So all actions happen in the same order, and the same global order, which could be one of those. Okay. The next level of consistency is eventual consistency. This one is the most, this is the weakest level of consistency, but also the highest level of availability and performance. It allows for temporary inconsistencies between nodes. It allows that nodes can have different values for the same, let's say, variables, or the same records, the same components or elements. All nodes will eventually have the same view of the data at some point in time in the future. This is what the assumption of eventual consistency. Eventually, given enough time in the future, all nodes will converge to the same state, which is a quite optimistic approach to consistency, to be honest. And it prioritizes, as we said, it prioritizes availability and performance over consistency. So here we are we care more about our nodes being available than serving or providing the correct data. That's why banks don't use that, or at least the critical bank operations probably are not using eventual consistency. There are three things here. Convergence. All nodes will eventually have the same state, and given enough time without new updates, all replicas become consistent. There is no guaranteed order, so it's up to the implementer to try to implement or to try to define actions in a way that order doesn't matter. And there's as we said, the different nodes may see updates in different orders, and no guarantee in what reaches what first. And then what we need to care about in this consistency model is conflict resolution. So because we are letting nodes diverge temporarily, we need to resolve conflicts, so to merge concurrent updates, for example, or conflicting updates. And we're going to see a few techniques later that we're going to use to resolve the conflicting updates, or to resolve conflicts. One example is last write wins. We just discard the previous values, but it's not a smart thing to do. In a few cases it works. For example, for very simple scalar values like numbers, maybe we shouldn't really worry about past values, but in most of cases we have to do a little bit more than that. And there's also merging where we manually merge the values of complex structures. or yeah, especially in complex structures where we have to merge. Okay, so yeah, this is an example of what can happen in eventual consistency. So client 1 writes x. X is propagated, or the new value of x is propagated to node B, but it takes a little bit of time to reach node C. So when client 3 is trying to reach, or is trying to get the value of x, the client gets the old value of x. But then, yeah. But then once the write is propagated to node C, then all the values become, become up to date. And some examples of this, of where this is used in, is in systems where availability is the most important thing. For example, S3. Apparently, S3 is using the same approach. So S3 would rather be out of date temporarily than be unavailable, and it makes sense. And we can also see it maybe in DNS, distributed caches. I mean, I would rather have a cache system that works rather than having a cache system that is unavailable because it tries to be to give me the latest value. But again, it depends on the implementation. But mostly in cases where availability matters the most, we use eventual consistency with some form of conflict resolution. Okay. Questions? Okay.
If the data, I had the problem. If we go for eventual consistency, like we will serve sometimes out of date data to the users, right?
Yes.
Okay.
Yeah. Okay. That's exactly what happens in this case. If you can see, the client 3 is trying to read old x. You see the line read old x. Client 3 is served the old value of x here. But if we go for this model, we should accept that. We should accept that eventually it will be updated, but yeah, I mean, availability is the highest, as we said. That's it. I hope that answers your question. Okay. Now we're gonna talk about, good to know lock-in mechanisms. We can talk about them later, a bit later in other chapters, I guess. But yeah, I mean, it's fine to have a look at them. Oh, no worries, no worries. That's all good. Yeah. So yeah, we can see pessimistic and optimistic locking. So this is an example of a database transaction, or of a database, database lock, which is a pessimistic locking. I think we all know what it means, or we all have seen it in some form. So this applies a lock, distributed lock, a real lock on all the resources in all the for everyone. So while the update, as you can see there, while the update is happening, no read or write can happen until the update is done. And yeah, I think there's not much to add here. But yeah, I mean, of course, this needs some some lock-in or the implementation of a distributed lock. Let's say I mean, it could be in some form of a mutex, or I mean, I think Zookeeper does that as well. Yeah, optimistic locking is also is an interesting way to do that, an interesting approach that yeah, I mean, keeps the data more available, but yeah, I mean, creates a bit of duplication or creates a bit of conflict resolution later, or tries to resolve conflict in a special way. So as you can see, like on the left hand side, Alice is reading from select ID amount from account where ID is equal to 1. So it's reading the initial value of account. Bob is reading also the initial value of account. Then, as you can see, an update is performed, right? When the update is performed, you can see that there is a very interesting version variable that we have here. The account was version 1. When the update was performed, the version was changed to 2. So we set the version as 2, where the version was 1. When other clients try to do the same, like I mean Alice here, it tries to set the same version because it's a concurrent call, because it's the last known version ID that Alice knows. The update fails because it couldn't find the version anymore, because the version was changed before. So it's a way to apply a form of an intentional fail, or an intentional failure of transaction or of update, where there is a mismatch of versions. So the Alice should read again, get the current version, then try to update. This is this is interesting, but also at the same time it has a few issues where one node could fail to write because everyone else is writing as well, or the data is being updated very frequently. This is not very good for locking in general is not good for frequent updates, but also optimistic locking is not good because a lot of transactions will fail, a lot of updates will fail, and they will have to be retried again. Yeah, but that was just good to know because we talked about locking earlier, so we're gonna talk about locks in the future as well. Yeah, now we can talk about replication. And when we mention replication, we talk mainly about replicas, or replicas means, or in layman's terms, it means I don't know, copies, or we can use it as a synonym of copies in some context. But the idea of replication is to have this same copy of data closer to users somehow, either logically or geographically, depends on the use case. But it's also we do it for that. We also do it for fault tolerance, and also scaling out for read and write when we have a higher traffic income. And and one of the we can see a few ways of or strategies of replication. There are synchronous and asynchronous replication strategies. We are going to see 2 of each. One of them we already seen, eventual consistency with conflict resolution. We're going to see more resolution techniques, but we're going to try to see the other ones as well. So synchronous replication, what do we mean by this? What we mean by synchronous replication is basically we're trying to have a strict consistency in replication as well. So we're trying to keep replicas, but we're trying to keep them consistent at all times. So one way to do that is a primary backup replication, or like a leader follower replication. So in this case, the backup is guaranteed to have the latest version of data at all times. So consistency is guaranteed here. We're talking about strict consistency. So what happens exactly is whenever a write request is sent to the primary, the transaction is also propagated to the backup. The same way that consistency, that strict consistency works. So if the replication fails, the transaction fails. And yeah, consistency is guaranteed in this case, but I mean, if primary fails, in this case, we have this, I mean, where primary fails, or yeah, and let's consider the case of databases. Primary or the leader gets disconnected. The backup, one of the backups is promoted to a leader, and we're gonna see. I mean, I think we're gonna see some of them in consensus, in the consensus chapter. But yeah, I mean, let's say we have one backup, the backup gets promoted to a leader, and then we don't need any data synchronization because the backup is always synchronized. Yeah, I mean, I think the way it's done in I think the way it's done in database systems is maybe a snapshot is taken, and then the follower, I mean, if you want to set up a new follower, or if you want to set up a new backup in case it fails, is a snapshot of the database is taken and then loaded, and then you get to replicate what's missing, or let's say from a kind of a log file. You can read from it, and you can see, the replica reads from the primary, and then then it becomes a follower, and in a leader follower structure, as you saw last time. Okay. Quorum-based replication. I think you're definitely gonna see that later, but it's a good opportunity to see this one as well in the consistency and replication. So suppose we have 3 replicas, or n replicas to generalize. If a write is acknowledged by W replicas, and we subsequently read from R replicas, and the sum of R and W is greater than the number of replicas that we have, then the read gets the updated value at least once. And this means if you have a number of writes, if your write has to be acknowledged, I mean, write doesn't succeed before it's acknowledged by W replicas, and the read is also only approved when it's validated by R replicas, and the sum of them is greater than n, which means that some nodes for reading and writing are overlapping. You're guaranteeing this. So there is a guarantee here that you're reading and writing from at least one replica. So one replica is a read and a write replica for you. And this guarantees that you're gonna see the updated value at least once. So let's say you have a value that has an update timestamp, and you attach this update timestamp and you assign it to all the replicas. You are getting the value from 2 replicas, for example. In this case, let's consider 2 to be a W and 2 to be R as well. 2 plus 2 is 4, is greater than 3, which is the number of replicas. So if we read from 2 and we write to 2, it means that we have a majority vote. We have a majority. When we read from one of the replicas that we are guaranteeing to have the latest value. So, for example, if we have 9 replicas, we are writing to 8. If we read from 2, we are guaranteeing that we are falling in one of those that has the latest write. This is the idea of the quorum-based replication. So if you have a number of replicas that you are reading from, and the number of replicas that you're writing from, in this case R and W, and the sum of them is greater than n, then it means that your read and write are overlapping. So yeah, and typically the R and W depends on the use case, but usually it's majority. So if you have 3, it's 2. So it's n plus 1 over 2 in odd numbers. So with this set, reads can tolerate n minus r unavailable or outdated replicas, and writes can only tolerate n minus w, which is a little hit to the availability of your distributed system, but it's it depends on the use case. But here what we can say is, let's say in this case we have 2, n minus r is 1, so 3 minus 2 is 1. We can only tolerate one replica to be unavailable or outdated. Let's say one replica goes down. That's all we can. That's all we can afford. Otherwise, we can't. We can't have acknowledgements. We can't have enough nodes to perform acknowledgements, which is which will render the whole system unavailable if we're using quorum-based replication, because we can't verify anymore, and that's one trade-off. So yeah, I think we'll talk about this. We'll talk about this in more detail in consensus in the consensus chapter, which is probably next. Yeah. Okay. Asynchronous. Oh yeah, I've had it.
What is the advantage of this architecture?
So, the advantage of this architecture is that you have you can guarantee a level of accuracy, and then you can guarantee even if the replicas, it's not necessary that all the replicas have the updated data, but you guarantee that you will see the updated data at least once. This is like a relaxed version of a full synchronization everywhere, so of a strict consistency. So if we had a strict consistency, R equals to W equals to N. All your read replicas, let's say, and all your write replicas, all replicas are write replicas and read replicas. But this is a relaxed, more or less relaxed version of a full synchronization everywhere, where you can guarantee for example, a replication lag, but only for a limited set of nodes. And this is like the advantage of using this is to have more or less consistency, but more availability than full synchronization. Yeah.
Yeah, it's clear. Thanks.
Okay, then now we talked about synchronous replication. Now we're doing it in a synchronous manner. Now we're gonna see how it's done asynchronously, and this is I think this is pretty common. So one of the ways, or one of the famous asynchronous replication techniques is gossip protocol. So each node has a set of adjacent nodes. I think you've seen how nodes could be adjacent in the past. In the communication chapter. So each node has a few adjacent nodes, and when a node receives updates, it propagates them, or every set, or every now and then, and it propagates the change to the adjacent nodes in the cluster, or if there is a cluster. This is used by the way, by Apache Cassandra. And yeah, I mean, this is the, I mean, it runs in the background, and for every node, for every node, it propagates the updates that it receives to the adjacent nodes, and then yeah, I mean, you can rely on this behavior so that eventually all the nodes will get the latest value. But it's not guaranteed, because some nodes can go offline, some nodes adjacent to the node we're trying to update can also go offline, and the node would never receive the new value. But yeah, I mean, there are also risks like this. And yeah, I mean, when you have stale nodes, there's what you can have, like anti-entropy protocol or anti-entropy strategy to try to prevent nodes from being isolated. So you can have multiple ways to do that. Like you can periodically exchange updates, for example, to prevent this. Or you can have I think in Apache Cassandra it runs every second or every few seconds to propagate the changes. So yeah, this is how this is how Gossip protocol works. Yeah, I mean, it's gossip. So yeah, I think it's the term is self-explanatory, but I mean, it's yeah, I mean, in a distributed system, this is how it works. And this is basically I'm not sure if you guessed it, but what kind of consistency that could fall into? Is it strict consistency, or
It's eventual consistency.
yeah, that's correct. It's pretty much it. It's an eventual consistency, because we don't stop anything. We don't try to achieve or try to guarantee any order of events happening. We're just relying on this this phenomenon of gossip to propagate our updates. Yeah, we already talked about eventual consistency with conflict resolution. This one, yeah, I mean, we talked about last right wins. Let's say, I mean, yeah, I mean, there is a simple value. I mean, simple calculated scalar value. Last right wins could be beneficial, or could be enough. Yeah, I mean, let's say in this case, we're taking every operation and we're putting a global timestamp. Let's, as we said, assume that timestamp is global. We timestamp it, and we consider the winner to be the latest update. But this, as you may have guessed, this could lead to data losses, because you're just discarding everything that was before, and it could be important not to discard it. And also maybe desynchronization, and we're gonna see the challenges with time. So yeah, this is not this is usually not the approach to take. I mean, another way to do it is merge functions. So instead of picking one winner, what if the result is a combination of all the previous update values? So yeah, I mean, consider the example of a Google Doc. So you go offline, you start writing some stuff. Another collaborator also starts writing some other content, and yeah, I mean, the merge function would try to take both of the, yeah, I mean, when you're back online, the merge function will try to take both of your inputs to try to generate one. Maybe this would result in sometimes unwanted things, because they have updated a word and you updated it as well. So this would, I think, probably in Google Docs, this would result in both words being concatenated with each other. So it's just, yeah, I mean, you change hello to hi, and then they change it to good evening, and then it's hi, good evening. So the concatenation of both. So yeah, I mean, you can implement your own merge function. It depends on the use case. But this is a domain specific. It's more, yeah. I mean, it's based on the application. It depends. I mean, we've said it depends many times, but this is what these kinds of these kinds of applications are about. Any questions so far? Okay. There is an interesting one. Is compensating transactions. Compensating transactions is when an unwanted transaction happens, or it's a type of a merge. It's trying to resolve conflicts by undoing the effects using some special kinds of updates, or using some something similar to a merge function. So we can see it in banking applications, for example, where conflicting transactions, let's say transaction happens twice, or conflicting transactions are rolled back. So it's like there is this batch that reconciliates the transactions. So أحمد قال لي نسيت الدارجة.
وي كنديروا هادشي انت بالدارجه صافي ولا شي هو سبحان الله.
اسمحوا لي
هادي يلا
ندرجوا شويه، نحاول ندرج والله تندرج.
راه درج.
اوكي غتقول application level resolution. اوكي دونك application level resolution كاينين some systems اللي it's very tricky ولا صعيب بزاف انك تاسيومي باللي راه زعما the updates will cause ولا will cause an issue ولا will not. It's very difficult to make those kind of assumptions في شي حوايج. So for example, when you have a very specific case that you want to deal with very specially, you just want to throw the conflict back to the application level, وتخلي the application level to take care of it the way it wants. Okay, إلا عندك conflict, you just say عندي conflict, and then the application should take care of it. Maybe you send both the values. إلا كان عندك multiple values ولا two, maybe you can say that you have a conflict, you flag it as a conflict or something. But in these cases, I mean that you leave it up to the implementation. You leave it up to the application layer. Yes, trade-offs. Well, I think you've guessed it. هضرنا على eventual consistency and kind of asynchronous replication. Before we go into a few examples that are interesting, كاينين a few trade-offs اللي they're part of the design. They're part of choosing the right solution. And for asynchronous replication, the trade-offs are there is a replication lag. So maybe readers will readers will probably see outdated values. So if it takes a long time باش propagate you one update. So I mean one solution to this is read your own writes. So and also consistent reads, or I mean one other thing that can happen is split brain. Database, let's suppose a leader got disconnected from the network. So replication lag. replication lag is a trade-off because when you go for asynchronous فاش كتختار انك دير asynchronous replication you you are choosing انك ما تكونش strict consistency because sorry log no lag sorry سنبدلو الفونت باش نديرو هذيك اللي كتكون باينه replication lag is yeah I mean that's the I think if it makes sense to you I think ماشي مشكل بلا ما نعاود نشرح but yeah replication lag here when we're going with asynchronous صافي we assume باللي it's gonna take some time to propagate the changes and sometimes it takes a significant amount of time depending on the application. Sometimes it takes minutes, sometimes it takes seconds, could be too much for the application. Split brain is I mean I think it's a special. There is a case in databases where the leader keep disconnected. We promote another follower as a leader, then the leader reappears to the network. وديك الساعة كيولي with the leader هذوك transactions that we thought were lost. Then we have a split brain. We have like a half distributed half blockchains. We're talking about a hard fork. Then you have واحد two subsystems اللي عندهم two different states, very different states. And ديك الساعة yeah I mean there needs to be a way to resolve this. Half hard fork I think it usually means that it's a new network ولا it means it needs to yeah I mean the transactions اللي غادي يكونوا في hard fork before it joins the network back غادي يكونوا lost. Sometimes some IDs are reused for the main network and we can't yeah I mean we have now replicas. I mean it can cause very very big inconsistencies for databases. But yeah. Okay, we're gonna see a few interesting examples. Jush, very interesting for me. Yeah, I mean we can see how MySQL provides replication in practice. واش synchronous ولا asynchronous, واش consistent ولا eventual ولا strict consistency ولا eventual consistency, and we're gonna see IPF. So not sure if you yeah you can see it. Yes, I think you can see it. Okay, so for some of the ways the MySQL guarantees or provides replication, source to replica. One of the replicas is the main, the leader. The others are followers. Okay, the source, and then there are multiple replicas. هنا كاين واحد decision ديال when to consider أن commit is done. There is the asynchronous way and there is the semi-synchronous way, and I think it's very interesting. Those two are very interesting examples. The asynchronous replication happens when we execute the let's say the insert. We added the insert into the binary log the source. It gets propagated to the relay logs, but at the same time we commit. We don't really follow the relay log. We don't really wait for the relay log to apply we don't wait for the transaction to be applied, for the update to be applied on the replicas. This is fully asynchronous. And then the statements will be re-executed independently for replica, which could fail, which means Yeah, I mean, it could have an issue, and a replica could fail to apply this for some reason. ولكن دابا in this case the primary actually the replica is desynchronized مع primary. Well, at least is lagging behind. And in that case, this semi-synchronous. We execute in the source in the primary. We publish we add to the bin log. It gets replicated relay logs, and then when it gets applied, then we send the commit. When we acknowledge that it's been applied, we send the commit. We call it semi-synchronous because we don't wait for all the commits to happen so that we can commit. This is not fully synchronous. It still could fail later, but it's the acknowledgement. The acknowledgement of applying it could be enough in some cases. So those are two interesting cases that we can see. Yeah, another way, or another example is IPFS, which is a very nice, a very nice example. So IPFS, I mean, this is a distributed file system. I think you're gonna see in the future Google file system, and it's quite similar approach to what we talked about Quorum. So every file is split into multiple chunks. Every chunk, let's say, so call it a CID, or each chunk has a CID, and the way it's explained here is the CIDs are available in some peers, and whom are downloading a CID, which we call it a pin. We pin the CID. So some peers and home CID. Some other peers and home CID, they're called candidates. Peers that could pin the CID eventually, but they still did not. The other peers that are already pinning the CID are called current. And there is a check, and it's interesting. We check if we are over pinning an item. If we have an item that is pinned more than it should be. So we have a few metrics, like how we regulate, and we see if we don't have enough pins. We pin the CID in multiple peers. إذا كانوا over pinning, we see if it's needed. We see if it's needed, we regulate it again, and we raise it depending on this replication factor. So this is a very interesting logic or piece of code. If you'd like to explore it. But yeah, I mean, it's very interesting how it's made, how this kind of logic is applied. Okay. Questions? Exactly. I should learn, go beyond the basic. I mean, I think we're just. I mean, Go is used a lot. So we can. Yeah, I mean, I think I think احنا كنمشيو for Go as the default language for this class. I don't understand. Anwar, can you share what you did with us? You mean slides or? Oh yeah, sure, of course. Yeah, I mean, as I said, it's very difficult to cover everything in 1 hour. We're trying to cover a large set of keywords, so you can at least have an idea. I don't know. Yeah, sure. I can share with you the specs. Yeah, sure. Any other questions? Oh yeah, sure. For me, no homework for the distributed part, for the distributed systems part. I would encourage you to, for now, to have a look at the IPFS implementation, and yeah. Ahmed, can you share the slides of the last session too?
هذا داكشي اللي كندير دابا، كنقاد الليست ديال ريسورسز سلايدز و الريكوردينغ. انا غنشريه دابا.
اوكي، غدير المونتاج ولا؟
لا لا لا، هذا ابلوديتهم دابا غنحطهم في ليست وصافي.
Okay. Then I'll stop the recording.